Hey, everybody, and welcome to week 5 of the economics of cryptocurrency. I'm going to start this lecture off by showing you a couple interesting websites and I'll circle back to one of them at the end too, but just to whet the palate in terms of today's lesson. One thing I wanted to show you is this is just a map showing essentially people who are currently active and part of the Bitcoin network, which is basically a global network of computers. Now, what's happening on these computers is these computers are essentially storing ledgers of transactions. And we've seen already in past lectures how banks store ledgers of transactions, and those can get complicated if transactions are happening between banks. Well, this is the cryptocurrency version of that. Instead of banks storing records of transactions, all of these different Bitcoin nodes are storing those records. They're also doing things like verifying transactions, which is what banks do. Um, they're also doing things like trying to figure out the order of transactions, which we'll talk about more really in this lecture. Another website is we can look at what's called the Bitcoin blockchain. We haven't gotten deeply into blockchains yet, but we really have built up most of the tools that we need to understand blockchains. Really, today's lecture is about putting those tools together in order to understand how the Bitcoin network specifically works. Once we understand that, it'll be a lot easier to understand how most cryptocurrency networks work. So what are these are called blocks, and blocks are essentially packages of transactions that record the history of transactions on the Bitcoin network. And essentially here we can find the entire history of the Bitcoin network. So let's go ahead and look at this block, which is, I believe, the most recent one. So yep, it was mined February 2nd, 2026. 5:47. I assume that's Mountain Time. I don't know if it's being updated to my IP, but that's probably Mountain Time because that's about 20 minutes ago. Now, the goal of Bitcoin is to mine a block on average every 10 minutes. We'll talk about how that occurs later and kind of get a little bit in that direction by the end of today's lecture. But what I want you to notice now is we can see some basic information of this block. These are all individual transactions that occurred on this block. So a block is a set of transactions that are all sort of confirmed when we say the block is mined. I don't expect you necessarily to understand exactly what that means yet, but just giving you a flavor for how this feels. So we have all these transactions here. We can scroll through. There's many different transactions. If we go to the last page, we see that there's 1,770 transactions, I think. Oh, so 1,771, because this is a transaction, I guess, at the bottom here too. A total of 3,081.46 Bitcoin or 239,648,556 at the current price of Bitcoin. So what we might call the exchange rate of Bitcoin between US dollars and Bitcoin. And so that's obviously a lot of money was transferred total. If we add up all those transactions, this is how much money flowed on this individual block. Um, so we can see, yep, right here it was mined 23 minutes ago, 16 seconds. And then just basic different information. Here is what's called the nonce, which will come up in today's lecture. Notice that very large number that is going to be an important aspect of Bitcoin. So this is 3,500,000,000. Just real quickly, remember just planting this idea of functions in your head. So what happens is all of the information on a block is hashed. And as we know, that leads to a fixed length output. However, certain hashes are necessary in order to mine a block. And so what these nodes, mining nodes, are trying to do is they want to mine a block because they earn some Bitcoin by doing that. And what they do is they adjust this number called the nonce, which leads to a different hash. Because remember, if we change the data on anything just a tiny bit, if we change the message just a tiny bit, we will get a very different hash. So what these miners do is they don't want to change the nature of the transactions because those are transactions that people are trying to engage in. So what they actually do is they simply change this number. Every time they change that number, they get a wildly different output from the hash. And then what that hash looks like essentially determines whether they will successfully mine the block. And a lot of today's lessons is getting into those issues. We'll return to this at the end of the lesson to maybe try to lock a little bit more of that in. So I'm going to work directly from the Colab today because all of the lesson basically lives in the Colab. Um, and what we're doing, so the past few weeks, like I said last week, we finished building up the main tools we need, which are supply and demand, some cryptography, some basics of finance that we now understand in order to really understand how the cryptocurrency system works. Now we're going to start getting into that understanding of how the cryptocurrency system actually works. And so first, I really want you to, you're a lot of this stuff you need to slow down and think about. I strongly encourage you to pause this video, stop, and think. We don't do that as much enough as human beings or students. Oftentimes we're trying to just like, oh, if I just read more or write more or work harder, then I'll understand more. Sometimes we do need to stop and think deeply about complicated things, and that leads to more true, deep understanding of some of these things. So I pasted this bold comment right at the top, and this is one that is really worth thinking about. In digital money, the coin, like a Bitcoin, is really a record of who owned it and when. So it's not a physical thing. We already know that. What it is, what a digital coin is, it's a complete record of its existence through time. And its value depends on agreement about that record. With a physical coin, on the other hand, ownership is verified by possession. If I'm holding a coin, everything we know, or really we assume, because it's possible that I stole the coin, and that certainly happens sometimes, people steal physical money. But the way that that system essentially works is if I'm holding the coin, we assume that whatever the history of that coin is, it led to my ownership. That's legitimate ownership. And then I can use the coin to buy something. Now, what would be a substitute for that in the digital world where there's not actually a physical coin? Displaying the entire history of movements of the coin would be a substitute for that. Now, before we get into blockchains and the digital version of this, I'd just like you to go through a thought exercise. What if we all lived in a little village that didn't use physical money, but instead used ledger money, so changes in a ledger? And the way that ledger worked, instead of having a bank, this village just has a really big poster in the middle of town with everybody's name and account balances of it. And every morning, everybody in the village shows up and they look and they say, okay, Gavin wants to give one coin to Sarah. And I raise my hand and say, yes, I agree. I plan on, and everybody observes me say that. Yep, I verify that that's what I want to do. That would be another way to manage resources in the society using a currency. Instead of having physical, just having a public record so everybody sees what's going on. The book mentions a very interesting example of this from Polynesia, where stones stacked in front of village huts were used. And these stones acted as currency. Sometimes the stones were so big that it was too costly to physically move them when they transferred ownership. And it would just be like, hey, everybody, I'm giving this stone to Sarah. And because I told everybody, everybody in the community respects that transition of value, even though we don't actually move the stone. Going even deeper, sometimes these communities would move to other islands and move their stones. Sometimes during those moves, stones would fall out of canoes if they capsized or something. But because it was public that this had occurred, everybody knew which stones Gavin owned. Even though they ended up at the bottom of the ocean, that ownership was still respected and was even used in transactions. Hey, Sarah, know that stone at the bottom of the ocean that nobody will ever be able to get that I own? I'm going to transfer that to you to buy some goods and services from you. And that system worked because A, it was public and everybody respected the history of that currency. And that's what physical currency actually does for us. We just never really had to think about it because it was physical currency. So we didn't have to do that much work to respect the history of that physical currency. Digital currency is an attempt to replace that. Cryptocurrencies are an attempt to replace that with something that's an anonymous bearer asset. It's a not necessarily. So instead of raising my hand and saying, yep, I confirm that I want to give that value to Sarah, we use a different set of rules for verification that allows for anonymity. Basically, in the account creation process, we make anonymity. To the extent that private keys are held privately, there's not an identity of a human being or a group or an agent tied to an account. So, what we observe on the Bitcoin blockchain are these addresses moving value to one another. So we can look at this address, for example. Or sorry, we can look at this transaction and what this transaction is moving around. It seems like Bitcoin, maybe I'm misreading that, but maybe moving Bitcoin to themselves. But that's the idea of these transactions. So 30 inputs into this one address. I don't know who owns this, and that's where the anonymity is, but I absolutely know that Bitcoin was moved from 30 different inputs to this address. So that's what is known. That's public. The transaction itself is very public by design because that's actually what creates verification. That's what gives us all an acceptance of this common history. So this list of transactions contained in these blocks present that common history, which gives us all faith, possibly, that this is a legitimate system and moving value legitimately between parties, at least from their perspective. I don't mean legitimately like they're not dealing drugs. I don't know what they're doing or why they're moving. And some of them are probably doing illegal activities, which is why, but from the agents using the system, it is a legitimate system, given some certain constraints hold, which we'll talk about today. Now, getting back to a very general idea from mainly microeconomics that we think about a lot, is that rules and incentives. So we have preferences. I want more money. I want more vacations. So if you give me vacations for less money, I'm more likely to engage in vacations. So I have preferences, and then those relate to my incentives. Those combine with rules to lead to outcomes. So, a central idea in economics is that outcomes are shaped by rules and incentives, not by intentions alone. That's extremely important and really relates to the first welfare theorem of economics. It's not just my intentions that lead to outcomes. It's my incentives mixing with rules and human incentives mixing with the rules of the game that lead to social outcomes. When we change the rules of a system, we change how people behave, and those behaviors produce the outcomes that we observe. That's sort of a core way of reasoning in economics. Not the only way of reasoning, but one of the main ways that economists explain the system outcomes. Why do we observe these outcomes? Because of the interaction between rules and incentives. Before looking at specific mechanisms, it is helpful to keep the desired outcome in mind for cryptocurrency systems. So the desired outcomes, because remember, we just said rules and incentive lead to outcomes. So if we have some desired outcomes, we might be able to, well, these are what these are the incentives that humans respond to. How might we set up the rules to get to those desired outcomes? So what are the outcomes that we want in a cryptocurrency system? Well, we want an anonymous bearer digital asset. And an anonymous bearer asset is like cash or coins because there's no connection to identity. But as we've discussed, getting that in the digital world might be more difficult. We've built some cryptographic tools that will likely help us get there, but that's one of the outcomes we desire is an anonymous bearer digital asset. Ownership controlled by cryptographic keys rather than accounts or identities. This is what gives us anonymity. So that's one of the outcomes that we desire. And also, we don't want to rely on a trusted central party, such as a bank or a mint, to basically keep the ledger for us. So those are the sort of things we're seeking in terms of outcomes. So we need to think about the rules of the game, of the cryptocurrency game that might lead to those outcomes. So everything we examine this in this notebook, which are things we now understand better because we've built them up for the last few weeks, are designed to move the cryptocurrency system towards that. We're not going to get quite all the way there yet in today's lecture, but we're going to move strongly in that direction. In the next blocks of code, rather than Bitcoin blocks on the Bitcoin blockchain, we will build up the logic step by step, starting with how transactions are authorized and publicly verified. Hopefully, that's a little bit of review from our last lecture, and then turning to the problem of transaction ordering. And we'll explain why that could be a problem, or remind you maybe of why that could be a problem. So first, creating accounts without identities. We saw how we might do this last time. In Bitcoin, there are no usernames, account registrations, or identity checks. Instead, our accounts are created cryptographically. How? Using public key cryptography. An account begins with a private key, as we saw last time. Public key cryptography begins with a private key, which is a large randomly generated number. And that hopefully is known only by its owner, or at least that's what would maintain anonymity if it was only known by its owner. From the private key, math is used to derive a public key. And then there exists a mathematical link between the private key and the public key. From the public key, an address is created. That address can be shared publicly because it's derived from the public key, which is public. This is then allows people to say, I want to send value or Bitcoin, for example, to that address. This is what others see in the network, and this is what receives funds. Addresses in the network receive funds. Remember, those addresses are derived from public keys. We saw last time we could do send a message to a specific public key, and then only the owner of the private key could read the message, for example. Really, the reason for addresses is it's a more succinct display of a public key. So importantly, addresses are not names. They could be. You could decide to attach your name to an address, but you don't have to. So you can remain anonymous. They do not, they are not identities, and they do not require permission to create. Now, some blockchains are permissioned. In general, all you should assume that I'm talking about permissionless blockchains like the Bitcoin network. You do not need permission to create an address to receive Bitcoin. Anyone can generate as many key pairs as they want because they're anonymous. So I could create a million addresses because my identity isn't tied to any of them. So you wouldn't even know if I was the one creating many of them. Maybe it would be to try to increase security from the perspective of the agent on the blockchain. Maybe they create many addresses and then pass Bitcoin from one address to another to to make it more difficult to see the history of those particular Bitcoin, because that type of information might be used to figure out identities later. This design achieves two goals. So anonymity, addresses are not inherently linked to real world identities. And bearer ownership, control depends only on possession of the private key, kind of like ownership depends on possession of the coin. Ownership depends on possession of the private key in this case. So an address functions like an account number, but without any bank behind it. Ownership is enforced by cryptography because we saw we can verify transactions using public keys rather than institutional records. In the next block, we will see how these keys and addresses are used to create and authorize transactions. And this one should be pretty much review from last time, I believe, because we showed how we could pass along messages. This is very similar. So first, we can create a private key. And then we can just use our library from above to generate private keys. And then from that private key, so we created a private key right here. Now that we have that private key, we can create a public key from it. So we reference the private key that we created right here. See, those are the same thing. And then we use a function called public key to create the associated public key. Because remember, those need to be linked mathematically. That's why we need to create this first in order to produce the public key from it. Now we want somebody to send this Bitcoin to or our cryptocurrency to, so we can make a recipient private key and a recipient public key in exactly the same manner as above. So this code is the same. All we're doing is the sender first and then the recipient. Then we serialize the recipient public key to represent an address. So this is how an address can be created. Recipient address is just for that public key. Public bytes is a function, and then just some encoding there to get it in the format that we'd like it in. So now we can have a message that essentially represents our transaction in this little Bitcoin. We are not actually sending Bitcoin or anything here, by the way. This is just a model, a toy sort of model of how this works. So transaction message, transfer ownership to recipient plus recipient address. Now we can hash that using apply a hash function to the message and the recipient address. That, of course, produces a digest, which is the output of a hash function again. And now the sender needs to sign the transaction. So the signature, the sender uses their private key and then use a function called sign to sign the transaction hash. And then we can print the transaction message truncated because it's pretty long now that we've created all of these other parts. Let's go and run all this so we can actually see those things being created. So transaction message, transfer ownership to recipient. There's an address. Transaction hash is here. Signature is there. And then verification, of course, we can verify it just like last time. Sender public key use the verify function. Signature, transaction hash, those are the inputs to that function. And then, yep, it is verified because it was signed by the correct private owner of the public key. So what we've done, basically, we just redid what we did in the last lecture. We have a cryptographically valid transaction. The sender authorized the transfer using a private key by digitally signing the transaction. Anyone can verify that authorization using the public key, right? Because right here, all we needed is a public key verify function, and the public key is public to anybody. We have this signature, which doesn't reveal anything that can be publicly accessed, and the transaction hash. And so anybody can do that step because the private key is not required in this step. The private key was required to make the signature, but it is not required to verify the signature. And no bank or central authority was involved in this transaction. However, we're still missing some pieces. Nothing here tells us whether this transaction was the first one What if only have one Bitcoin and I want to buy 10 Bitcoins worth of stuff? I might try to send the same Bitcoin to 10 different people. This is called the double spending problem. You sort of saw how this problem might show up using traditional banking, traditional digital currency, or digital um, money systems in ledgers. If we don't look at the accounts till the end of the day to net out transactions till the end of the day, you saw in your homework that we could lead to a pretty big double spending problem within that day because we're not keeping up with the verifications. So this is what we really have to begin to understand now is how are we going to stop people on this big network from sending the same Bitcoin to many different people? Because they would definitely have an incentive to do that, to double spend their money. Because obviously you can get more bang for your buck if you can spend the same buck on more than one bang, which we don't want. That would not be a valid currency system, though. That would not work. So, however, nothing here tells us whether this transaction is the first one, because essentially we want to say, okay, we'll let the first time Gavin wants to spend a Bitcoin go, but if he tries to spend the same Bitcoin again, we wouldn't want to allow that transaction. So the same sender could create another transaction, spending the same asset, that's where the problem is, signed just as validly. Because all of this doesn't say anything about have you ever spent this before? We're not verifying anything about that in the above. Digital signatures solve the problem of authorization. Yeah, Gavin authorizes this transaction, but they do not solve the problem of ordering. Which transaction goes first if this person's trying to overspend their assets? This gap deciding which valid transaction counts is central to the economic cryptocurrency problem that cryptocurrencies must address next. So we have verification so far. We can sign and authorize transactions. Anybody can authorize them. Now the question is, well, like, how do we keep people from the what's called the double spending problem? So A, people have an incentive to do it, double spend their cryptocurrency. We need a rule that leads to an outcome where they don't double spend the cryptocurrency. Or a set of rules is probably a better way to say that. So let's just see that this would work, that both would be valid. So sender private key, sender public key, recipient A, recipient B. So now all we're doing is now we have two different recipients, create two conflicting transactions, transfer coin to recipient A, transfer coin to recipient B. The assumption, of course, this is the same coin that I'm sending to two different people now. Hash and get the digest. This is all the same. Sign them. Both of these are valid transactions. So I successfully essentially sent my single coin twice without having more than one coin. So this is a problem. So this block of code just shows that this so far we haven't solved the double spending problem just with cryptography. And actually we're not going to apply cryptography really to send this problem. We're going to use tools that are from cryptography, but really not the point is not cryptography when we apply these rules. So this gets at essentially why transactions must be public. Because now imagine I'm out in that village. It's like I will send my coin to Sarah and I will send my coin to Alice. The other people in the crowd will say, you cannot send the same coin to two different people. That is what would stop the ordering problem in that case, right? The public who can observe the transactions on the poster or the billboard would notice that I was trying to double spend. That gets us at how we're going to think about solving this double spending problem on a cryptocurrency network, which is why transactions must be public. Because remember here, individuals, these addresses are random people, or I shouldn't say random people, they're not necessarily random people, they are anonymous people, but all of the transactions they are making are not anonymous. Transactions are public. Why transactions must be public. We just saw that two conflicting transactions can both be cryptographically valid, so we haven't solved that problem cryptographically. If participants only see transactions individually, there is no way to detect double spending. So to address this, Bitcoin requires that transactions be publicly announced. Right there, there's the publicly announced transactions that made it onto this block. They're publicly announced before they end up on a block, by the way. Public visibility serves two purposes. It allows everyone to detect conflicting transactions, like, hey, Gavin tried to send this same coin to two different people, and it makes double spending observable rather than hidden. Really, these are the same problem, honestly. However, public visibility alone is not enough. Even if everyone can see all transactions, the system must still answer a crucial question. Which valid transaction came first? Because what if I try to send Bitcoin on there? You don't know who I am. You can't really back out of this. The network has to decide how to deal with this. For example, when Bob and Alice were making bets in that last homework, which bets should be paid and which ones should not be paid. In that case, the bank would probably say, well, they ran out of money at this point, so they're going to pay the bets before this point and not pay the bets after this point. It's in a decentralized system, that's a little bit trickier to get at because there's not a central authority to just use a very specific rule to decide which one came first. Now, essentially, what happens is transactions go out to all these different nodes to be verified like they were above, cryptographically verified. Well, because of the way that digital network works, namely the internet, it's not clear that nodes will receive transactions in the same order. So one node might receive Gavin sends Alice one coin first, Gavin sends Alice same coin second, or Sarah same coin second. Over here, Gavin sends Sarah coin first, Alice same coin second. So you might get two different nodes who actually receive the transactions at different points in time. Seeing conflicts does not resolve them. Public announcement allows direction, but it does not create agreement. So if everybody shows up at the village board and sees that I've tried to send the same coin to two different people, how are we going to decide who actually gets the coin if there's not an obvious order in that transaction? So now this shifts the problem from authorization, which we've done. We've figured out how to authorize to ordering. What order should transactions occur in? So authorization, as we've seen a couple times now, is handled by digital signatures, signing with private keys. Then those can be verified because of public key cryptography. But ordering requires a shared history of transactions, a publicly agreed upon shared history. In the next block, we will see how transactions are grouped and organized to begin addressing this ordering problem. So we have all of these transactions floating around. Basically, people propose transactions. That public network is running the Bitcoin core software or other related software. That software will automatically verify, check digital signatures for verification. Invalid transactions will be blunted at that stage. Once those transactions become verified, we should think of those as pending transactions. Banks kind of use pending transactions in a similar way. This is a pending transaction because we've verified that the sender wants to send it. What we have not done yet is verified that the sender will have enough funds to actually make this transaction. So that ordering is sort of the same in the traditional digital banking system and the cryptocurrency system. So if transactions are publicly announced, the system needs a way to organize them into a shared record, the ledger that banks normally traditionally play the role of, but now we want to do this without a central authority like a bank. Bitcoin does this by grouping transactions into blocks. Here's a block, which essentially is a group of, we saw about 1,800 transactions. Grouping in transactions into blocks helps for a couple of reasons. Many transactions can be verified together, so there's a little bit of efficiency gain there. So we're not just like putting every single transaction alone on the blockchain. Participants can reason about chunks of history rather than individual messages, so it just makes verification of this shared history a little bit easier and more efficient. And ordering can begin to be discussed at the level of blocks rather than just single transactions, which is going to make our life a little bit more efficient and easier. At this stage, notice what blocks do not yet solve, though. They do not decide which block should be accepted, because what if there's different blocks floating around and those have inconsistent, they have verified transactions on them, but maybe one of those blocks has my coin going to Sarah, a different block has it going to Alice. If both of those blocks are mined and put into the shared history, that's an issue because we've allowed double spending on our shared history. That does not work with what we're trying to get, which is our anonymous bearer asset, the coin, because now two coins have been created out of one in that shared history. That's obviously an issue. So blocks are a way to structure information, but not yet a way to enforce agreement. So the one remaining question is, who gets to propose the next block and why should others accept it? So one thing is like if everybody could just propose blocks for free all the time, that would become an issue because it's like, well, everybody's just going to try to propose blocks. Like I'll propose a block where everybody's just giving me their Bitcoin. Now I can't really do that because that would fail at the transaction verification stage. But I might propose a block where I give one Bitcoin to all of these different people on Earth, and then they give me tons of money in exchange for that Bitcoin. So I've become infinitely rich with one Bitcoin by just giving the same Bitcoin to everybody. So if I could just do that costlessly, I would want to do that. And so I can download the Bitcoin Core software onto my computer and start verifying transactions, combining transactions onto blocks and then sending that block out to other nodes saying, hey, verify my block. So maybe what I'd want to do is I'd write down that block. I'd say, here's a block where I give my one Bitcoin to 1,800 different people, and they all give me, I'm going to give them a sweet discount. They're going to give me $10,000 per Bitcoin. Okay, I've gotten myself a huge payday by just selling my one Bitcoin to tons of different people. So what would make that more difficult? Well, if I had to pay and fight for basically making new blocks, then that would at least would give me some cost in terms of proposing double spending blocks like the one I just proposed. So the Bitcoin system uses something called proof of work, which creates a cost to the idea of putting these blocks together and mining them, putting transactions on a block, proposing that that be the next block in the shared history that is the Bitcoin blockchain. So once transactions are grouped into blocks, that is groups of verified pending transactions. So these have the digital signatures have been verified on these. Now we're going to package them together into a block. The system needs a rule for who is allowed to propose sort of the next block on the system. And we don't, because we don't want this to be a central authority. So who's going to do it? Bitcoin uses what's called proof of work. This is the most commonly used um, costly block proposal system on blockchains. Not the only one, by the way. And there's a lot of change around that since the book came out that we're reading and in more recent times because proof of work takes a lot of energy basically and a lot of computational power. And so there might be substitutes that are more efficient in terms of the actual cost. So under proof of work, proposing a block requires solving a computational puzzle. The puzzle is costly to solve, but easy to verify. So this comes up, this idea of part of something is costly, but part of something is easy. That reminds us of hash functions a little bit and other things from cryptography. That is also an aspect of blocks on a blockchain. So whatever this proof of work system is, it's something that's costly to solve to get the right answer, but it's easy to verify if somebody has in fact gotten the right answer. And the cost is paid in real resources. In the case of proof of work, it's time, time is money, and computing power. Computing power takes energy resources and hardware, so you have to invest in it. It is costly. There are opportunity costs. You can throw computing power at things other than mining blocks on a cryptocurrency blockchain. So these are real costs that need to be dedicated in order to mine blocks. This rule matters economically because it ties influence in the system to costly action. If I want to have influence on the cryptocurrency blockchain, I have to invest in this cost. I have to pay this cost, but I don't have to reveal my identity. Why something like this helps get us to this ordering issue. Proof of work addresses a key vulnerability in decentralized systems, so Sybil attacks. A Sybil attack occurs when someone creates many fake identities to gain influence over the system. So, like we already said, I could make a million addresses because they're anonymous. Maybe somebody says, like, we should have a democratic blockchain and every address should get one vote. Well, that would be immediately susceptible to a Sybil attack because I would go make a billion addresses and then I'd have a billion votes. You don't know that I'm the person with a billion addresses because you don't tie identity to addresses. So if instead, and then I could gain influence, like I vote that we mine this block where I paid a million people with one coin. If I have one vote, one address, maybe I have the ability to do that because I'll just keep printing addresses. I'll just write a loop in Python that just gives me an infinite number of addresses. Then I'll control the system and then I'll destroy the system basically by double spending. That's a Sybil attack. So, however, if I have to use costly resources, and it turns out that I would have to use so many resources in terms of computing power and time on average that I was dedicating more than 50% of the overall resources to the system. That's how much I would need to invest to kill the system. So that what that means, that is an important outcome, is that the size of the net, if this network is huge and there's many different nodes, it's very difficult for an individual actor to become more than half of the total computing power on the network. If they did, that would be what's called a 51% attack, and that would destroy the network. But the network is so huge at this point that it would be incredibly difficult to become that powerful on the network. So a Sybil attack occurs when somebody creates many fake identities. So for example, suppose an attacker wants to double spend, like my block where I say give the same Bitcoin to many different people. They send a transaction paying a merchant, then try to convince the network to accept a different transaction that sends the same funds back to themselves. If influence were based on voting, for example, the attacker could create thousands of fake nodes. So thousands of these fake nodes. And then they could just simply vote for their preferred version of history. And of course, if everybody's just doing that, that's not going to be a system that works. That just leads to incentives. Everybody's just trying to print as many identities as possible so that they have as many votes as possible. That is not going to be a working system to create the shared history that the value of the digital currency is derived from. But proof of work makes this very costly because identities are cheap. That's true. You can make as many as you want, but solving the puzzle in order to mine a block of transactions is not cheap. It's computationally expensive. Creating many identities does not help unless the attacker also controls significant computing resources. So what proof of work gets us to, but we still aren't all the way there yet. So proof of work limits spam and manipulation, makes block proposals costly, and creates a barrier to attacking the system. However, proof of work alone does not decide which block is ultimately accepted or how conflicts between blocks are resolved. So it determines who can propose blocks, but not yet which history wins. Because again, remember, transactions could show up at different nodes in different orders. We could get inconsistent transactions on different blocks. So which one of those blocks will become part of the shared history? That's where we'll have the order, the shared history order, which we need. We're not quite there yet. We needed some additional rules that we'll go over in the next lecture to get there. But before that, let's just walk through how the proof of work part works. So in Bitcoin, proof of work is implemented by requiring miners, so people that want to propose new blocks, which again are just the next step in the history of that system. So the idea being, let's see, did a new one come yet? It probably did. So yeah, this block was mine. Now the most recent one was 5 minutes ago. So while I've been talking to you, maybe actually two have been mined since I've been talking to you. Now, who got to mine that? Why did this block get mined? That one's going to have, just so we can see it, here's the nonce on that one. So that's a slightly different number than we had before. And that's going to determine whether you get to mine the block. We're going to search for a nonce that that causes something to happen. So in Bitcoin, proof of work is implemented by requiring miners to find a value called a nonce, that number we were looking at, such that the hash of the block, because we're going to hash the block essentially, that's a way to make this shared history a little bit more manageable. Because we know that even though that block has tons of data on it, if we hash it, it leads to this fixed length value, satisfies a specific condition. In Bitcoin's actual system, the hash must be below a target value, which determines difficulty. So we hash a block that leads to a fixed length output, but we know that that output changes dramatically every time we change any tiny part of the block. For example, by updating this number called the nonce, if I just change that by 1 unit, I'm going to get a totally different hash. And so this is equivalent to requiring the hash to begin with a certain number of leading zeros, by the way. That's one way to think about it. And let's see if we can find so right here is the hash. Notice that in order to be the miner that wins the block, you basically keep iterating this nonce number, which gives you a different hash every time. And eventually, if you do that enough times, like billions of times, you will get a hash that's like this, that has a bunch of zeros at the beginning. Whoever gets that first gets to mine the block. That is the proof of work game that's going on. Is we have a bunch of different miners throwing computing resources at hashing this block by updating the nonce, rehashing, seeing what they get, the software checking. Does this have enough leading zeros to win? No, it doesn't. Change the nonce by 1, hash it again, see if you get the right number of leading zeros. Eventually, somebody wins that race. They're the one that gets to mine the block. So doing that is computationally costly because you basically have to hash something over and over and over again, billions of times to try to win this race. Many people are engaged in this race. So finding such a hash is computationally costly. But checking that the condition is satisfied is very easy. We just checked it. Yep, the condition was satisfied based on this because if you hash this entire block, this is the hash that they got. Now, I'm not explicitly checking it because I'm not hashing it everything and making sure that that's true, but that is happening. The many nodes are doing that to verify that this is a valid block. So in mathematical terms, the proof of work condition is applying this hash function to the block data and the nonce, which is the thing that's changing, because they're not going to change the block data. Those are the valid transactions. So we need something to change. That's what the nonce is doing. Number once is what it's short for. And that has to be less than some target value tau. Now, the Bitcoin network will actually vary this target value over time. So if there's more miners, if there's more computational power being thrown at the Bitcoin network, then achieving this will happen quicker. When there's less computational power being on the network, achieving this will take longer. So Bitcoin's goal is to mine a block on average every 10 minutes. So over time, the target value is updated to try to achieve the goal of 10 minutes iterations between block on average. So we already saw these blocks aren't happening exactly every 10 minutes, but it's pretty close, and that's what the target is. If all of them end up being too fast, the Bitcoin network will make the target value condition more difficult. If they're taking too long, it'll make it easier to try to keep that target of mining blocks every 10 minutes. So this is just a specific hash function, the one that Bitcoin network uses. The nonce is a value chosen by the miner, and tau is the target value. A lower tau makes the condition harder to satisfy because there's a smaller range of valid numbers of valid outputs to reach. A bigger tau makes it an easier condition. The important idea is not the exact puzzle Bitcoin uses, but the asymmetry. So it's hard to produce and it's easy to verify. So again, in terms of like the economic rules that lead these incentives, that's ultimately what we care about. So let's just implement a simplified version of this. So a little toy proof of work example. So we're going to define a function that's a mine with leading zero. So we have block data, difficulty, and a maximum number of tries. This is just going to see how long it takes to find one of these values. We're using a much easier condition than Bitcoin is. And then we have the difficulties right here. So we have on Bitcoin, um, this is literally defining the number of leading zeros. So we're only looking for two zeros at the beginning of the hash digest or four. We're doing two for purposes of comparison. So we already ran that. Let's go down here and see what happened. So the one with the difficulty of two, here's our hash. It has two leading zeros. It took 0.0001 seconds to get that one. So that's not difficult enough for the Bitcoin network. And it took 32 tries. So we had to change that nonce 32 times, which is happening in this code right here. Just add one to it and then rehash it again. Keep going through that loop until you find a hash with two zeros at the beginning. And then we said we're going to do another one that needs four leading zeros. That took 0.1937 seconds. So an extremely short amount of time, but much slower than this one. That took about 150,000 tries before we got four leading zeros. So we can see how we can use this proof of work to vary the computational resources necessary to mine these blocks and make this proof of work incentive scheme. So we still need a couple more pieces because what happens if an attacker comes to the system and tries to mine invalid blocks? And then all of a sudden there's two valid blocks floating around the system. How does the system choose which history is going to be the common public history that they share? So again, just coming back to this, we see all these blocks that literally define the entire Bitcoin history. And then each of those has many transactions for the most part on them. You could go all the way back to the very first Bitcoin block on this. I encourage you to poke around on this, get used to it, see the different type of information that's available about the Bitcoin system here. You will be doing something with proof of work just with this last chunk of code in your homework this week. So please let me know if you have any questions about that. I'm always happy to meet about the collab assignments. Some people are doing great on those. Some people are struggling a little bit. If you're struggling a little bit, please just reach out to me. I'm happy to help you with it as much as I can. Email me. I'm happy to meet virtually or face to face. So have a good week, and I'll see you next time.